The third part of 4-2 is binomial distribution. So I realize there's a lot of stuff in this section. That's why I took 3 lessons to teach it. But the last part of 4-2, so 4-2 part C here, is how to graph a binomial distribution. So the first thing we did was we learned how to compute a binomial distribution using the formula. And then we learned to calculate binomial distribution probability using the table, make it a little bit easier. And then finally, once we have all of those probabilities, how do we graph it? How do we represent it to everybody of everything that can happen? Okay, so here's kind of the thing. So hopefully by now you know what P is, you know what R is, you know what N is. So where do we put those? We place the R values on the horizontal axis, the x-axis. So 0, if I had 5 puppies, right? If I had 5 puppies, my x-axis would be 0 puppies, 1 puppy, 2 puppy, 3 puppy, 4 puppy, or 5 of the 5 puppies. My probability, right, this means probability, my probability of 3 of the puppies, 4 of the puppies would then be on my y-axis. My y-axis is the probability. And this is going to look like a histogram. So if you remember from a couple of chapters ago, when you get done, it should look something like this, right? And this would be like 0 puppies, 1, 2, 3, and then the probability over here. 20%, 30%, 10%, and so on. Okay, so it's going to look very similar to the histogram we've done before. Since this is a discrete variable, not continuous, you extend by a half either way, but a bar is going to represent 3 of the 5 puppies. You can't have 3.2 puppies. So each bar is going to represent that R out of the N. Okay, so let's do an example. That's probably the easiest way to understand this. A biologist is studying a hybrid tomato. It is known that the seeds of this hybrid tomato have probability of 70%. So I want to underline that. That's my P of germinating. The biologist plants 6 seeds. So there's my N. Make a graph of the binomial probability distribution that shows the probabilities of all the way to 6, right? Here's all of the R's that can happen out of 6 seeds to germinate, okay? So the first thing I need is my book again, your table in A8. And the reason I can use my book, my table, is because I have a 70% probability. I have a nice probability to use, so I can go ahead and use my book. If I didn't, if this was maybe 72%, then I would have to use the formula to calculate each one. Okay, so 70%, and my N is 6. So I'm looking on A8 here. N is 6, and all the way over to 70%. And I want every single one. So I'm going to make that probability distribution table first. I'm going to have my R be 0, 1, 2, 3, 4, 5, 6. And then I'm going to do the probability of each one. So 0, let's see, I need 70%. 70% for 6. 0 is 0.001. 1 out of the 6 would be 0.01. 0.06. I'm just going down the column. 0.185. 4 of the 6 at 70%. 0.324. 0.303, and 0.118. Okay, that is all the information I need for my table. That is it. So now if I start graphing, and again, my x-axis, I'm going to have 0 through 6. So 0, 1, 2, 3, 4, 5, 6. And my y-axis is going to be the probabilities. And if you look at your probabilities over here, the highest probability is 32%. So let's count by maybe 5s. 5, 10, 15, 20, 25, 30, 35. okay? And you graph it just like you did the histogram. So I know 0 out of the 6 seeds is 0.0, that's 0.1%, so barely nothing. Oh, my marker's off. Okay, 1 would be, move it right to 1%. 2 is 6%. And 3 is 18%. Four is 32.4. 5 is 30. And 6 is 11.8. And I apologize if that looks a little bit off. My marker is off. I should have realigned my board, but you guys get the idea. Sometimes in statistics, if it is maybe hard to read to the reader and you really want to get those percents across, what you'll see in statistics sometimes is that the statistician will actually label the percent on top of it to give the reader a really good idea of what that percent is, if they want to be more precise to the reader. So that's optional, you don't have to, but what you do have to do is what? Label. Yep, you need to label. This would be number of seeds. This would be probability of germination. And I would need a title. I would do hybrid tomato probability of germination. Something like that. Okay, so labels title. That's a binomial graph, a binomial probability graph, binomial distribution graph. Okay, so what we can add to this, we can add an expected value, a mean. We can add standard deviation. What's the spread look like? And we have a couple of formulas for those. My formula for mean, and it's actually quite simple. You guys can't see that. Let me write it up here. My formula for mean is n times p. And my formula for standard deviation is the square root of NPQ. Okay, so very simple. This is called the average, your average number of seeds to germinate, or the expected value of seeds to germinate. It'll also be read that way. Standard deviation is just standard deviation. So if I wanted to calculate the mean and standard deviation for this problem, I could say that my mean is 6, because that's my n, 6 times 0.7, and my standard deviation would be the square root of 6 times 0.7 times 0.3, right? Because if my p is 70%, what's my q? 30%, yes. So taking my calculator, 6 times 0.7, so my average seeds germinating is 4.2, and that should make sense, especially looking at my graph. 4 was the highest probability. So for 4.2 seeds to germinate on average, that sounds correct. And then my standard deviation, you should be thinking, oh, it should be small. My spread is only going from 0 to 6. And I get 1.12. Okay. So that's the other thing you can calculate after you have this information is mean standard deviation. Let's try one more example. It is estimated that 75% of grapefruit crop is good. The other 25% have rotten centers and cannot be detected unless the grapefruit are cut open. Anyone that eats bags of oranges or apples or grapefruit know this, right? You cut into it and you don't know till you cut into it that, it's a bad one, okay? So make a histogram of the probability distribution for R. Okay, so let's do that first. So what I'm going to have, I'm going to have a probability down here. Let me zoom out a little bit so we can see it better. There we go. So here I'm going to make my my R and P of R. Right, so 0, 1, 2, 3, 4. I'm going to run out of room. Let's see. Let's do it this way. And then my P of R. I need my table again because it's 75%. 75% for 10. So 75% for 10. And I need them all. So that would be 0, 0, 0. And then 0.003, 0.016, 0.058, 0.146, 0.25, 0.282, 0.188, and 0.056. And then I can use that information to graph. Right, so I'd go 0 through 10. And I know my probabilities, the biggest probability I have is 28%. So I count by fives again. 5, 10, 15, 20, 25, 30. So then 0%, I'm just going to highlight here because 0% means nothing. 3 is barely anything again. 4 is 1%. Finally, 5 is 5.8, so that finally we get a little bit more there. 6 is 14.6. 7 is 25. 8 is 28.2. And then we start going back down. 19 is 18.8. And 10 is 5.6. Okay, so you get the idea. I know it's not very good. I'm trying to fit everything on one board, on one slide here, so you guys can see it all. But you should know these graphs well enough that you should know what it looks like. Titles and labels, yes, you do need those. So I would label the x-axis probably number of grapefruit. And then the y-axis would be probability of good grapefruit. And then I would need a title. I would say good grapefruit in a sack of 10. Okay. So there is our probability histogram of the probability distribution. That's what we just did. That's what that is, right? We found the probability of every single R out of the N and then made a graph. Okay, so what else can we do with this is we can use all this information that we wrote down right here to figure out some probabilities. what is the probability of getting no more than one bad grapefruit in a sack? So no more than one bad grapefruit. That would be one bad grapefruit or none, okay? This is, remember, good grapefruit. So you have to think opposite. If I have 10 good grapefruit, that's 0 bad. And if I have 9 good grapefruit, that's 1 bad. So to answer that first question, I would add these two probabilities, because this would be 1 bad grapefruit and 0 bad grapefruit, because that's what it's asking, bad grapefruit. So part A here, I would take 0.188 plus 0.056 and get what? 0.244. Part B, what's the probability of getting at least one good grapefruit? At least one good grapefruit would be here. At least one good all the way to 10, right? At least one means one or more. And what you should notice is the complement. The complement to that of at least one is none. So I can do 1 minus none, and the probability of none good grapefruit is 0. So this would be approximately 100%. Approximately 100% chance if you buy 10 grapefruit, at least one of them will be edible. Okay, so now the new part that we kind of talked about, what is the expected number of good grapefruit? That's an average. Expected number is the same thing as an average, and that's n times p. N in this case is 10, p is 0.75, so we can expect 7.5 good grapefruit. Okay, what's the standard deviation? Standard deviation is the square root of NPQ. So if I did 10 times 0.75, what's Q then? 0.25. So take 10 times 0.75 times 0.25, square root that, and you get 1.37. So my expected value, my mean, is 7.5, and my standard deviation is 1.37. Should we do one more? "75% of foreign-made autos sold in the United States are now falling apart. Determine the probability distribution of these autos falling apart in a random sample of 5 cars." So if I have 5 cars, I would have this, right? My R and my probability, 0, 1, 2, 3, 4, 5. Probability, 75%. But I only have 5 cars, so 75% with 5. So 0.001, 0.015, 0.088, 0.264, 0.396, and 0.237. Okay. That would be my probability distributions of X. That's what I just did. Okay? So draw a histogram of that. I'm going to have 0, and probability, my biggest probability is 39, so maybe count by tens. Draw each one, so that's 0.1%, so pretty much nothing there. 1.5%, 8.8%, 26%, 39%, and 23.7%. Okay. Of course, we need some titles and labels. So this would be number of autos. This would be probability falling apart. And my title would be Autos since 1984. Oh, foreign, I probably need foreign made. That's probably important, right? Foreign made. If I was reading this graph as a reader, I would want to know it's foreign made auto since 1984 that are falling apart. And some titles are going to be lengthy, but a title should be what you need it to be for the reader to understand. Okay, sometimes short titles aren't always feasible because it doesn't make sense. You need a title that lets the reader know what you're talking about. The mean, then, expected value, right? Calculate the mean and standard deviation. Mean would be NP, which would be 5 times 0.75. And my standard deviation would be the square root of 5 times 0.75 times 0.25. Right? Because if P is 75, Q would be 25. So calculator, 5 times 75. Standard deviation then. And should my standard deviation be small? Yes, I'm only going from 0 to 5. So 0.97. Okay, so homework for this section is again 4-2. So 4-2 in your book. What page is that? Page, we're going to do page 212. So homework 4-2, this is part C. So after this, you should have part A, B, and C all ready to hand in to me, either probably through email, scan, or take pictures. Page 212. And you're going to do 23 through 26. But I have some directions again. 23 and 24, you're going to use the formula. Okay, you need to use the formula. On 25, I'm changing that to 35%. And on 26, I'm changing that to, 25 is 45%. And 26 is 35%. I'm changing those so you can use the table, but I still want you to practice using that formula again. And then you are doing parts A, B, and C that the book says, parts A, B, and C. And you're going to calculate the mean and standard deviation for each. Okay? The big thing you need to know in this is that anything unusual is less than 5%. If you remember that, let me refresh your memory. Unusual is less than 5%, or another way to consider something unusual is that it's more than 2 standard deviations from the mean. Right? So if you have the mean, and add 2 standard deviations to it, and subtract 2 standard deviations, anything more or less than that would be considered unusual.